So it's my pleasure to welcome Sukyoung Ryu from KAIST, the Korean Advanced Institute on Science and Technology. So Sukyoung is a professor at KAIST and doing a lot of interesting work on analysis of Android applications, JavaScript, and recently on blockchain. So previously to KAIST, she was in the US working at Sun Microsystems Labs, research labs, working on Fortress, interesting programming language developed there. And before she was a research associate at Harvard University. So I'm looking forward to the talk. Go ahead.
Thank you. Hi, I'm Sukyoung Ryu from KAIST Korea. And the title of today's talk is Vulnerable Semantics of Solidity. But because this work is in progress and this talk is being recorded, I changed the title to Fortress, JavaScript, and Solidity. So these three languages are the main languages that I have been playing with for the last more than 10 years. So I will give you a little bit of background of me in terms of programming languages. So this is when I was a graduate student at KAIST. I was working on static analysis of languages with exceptions, just like ML, standard ML, Objective-Camel, and Java, things like that. But the main implementation language for me was SML and OCaml. After that, I was a postdoc in, research associate at Harvard, and I was working with this Norman Ramsey, working on the debugging everywhere project. And again, the implementation language for me was assembly, C, and Modular 3. Have you heard of Modular 3? And then I moved to Sun Microsystems Labs, led by Guy Steele. And we were working on, we designed and developed a new programming language called Fortress. In that project, the implementation language for us was mainly Java and then Scala. So Scala was our loved language. Because at some point, we had two graduate students who were hired to implement type system for Fortress, and that is really advanced. So we got two awesome graduate students, and they tried to implement the type system in Java for 3 months and failed. But because they were so good, we hired them again in a year later, and we switched the language to Scala. And they successfully implemented that in 1 month, and the size of the implementation in Scala was 1/3 of the incomplete version of Java. So after that, we switched most of the things in Scala. Then, what is Fortress? So Fortress is a multi-core language for scientists and engineers. It's a multi-core language in a sense that almost every language construct is run in parallel. So this is a code example in Fortress. Every underlined part is run in parallel. If you want to run it sequential, then you need to say sequential. And that is for scientists and engineers, meaning that we tried really hard to support mathematical notation, because that's the language for scientists and engineers. So our slogan was, run your whiteboard in parallel. So the three main characteristics of Fortress was parallelism by default, mathematical notation, and growable language. And this third characteristic is really important. And this was inspired by Guy Steele's Uppsala 1998 keynote talk, which is also still available at YouTube. And it was so good, so the talk script was published as a journal paper. And I particularly like this video by Martin Udersky. When Martin is introducing the Scala programming language, he introduced it as a scalable language, which was, again, inspired by Guy's invited talk, a keynote talk in Uppsala 1998. And during this talk, which is also available at YouTube, Martin says, Guy's talk is an absolute piece of beauty. So I strongly recommend you to take a look at his talk. It's really awesome. So that's the Fortress programming language. We started the design and implementation of this Fortress from scratch. It's from specification. You'd better have a language specification, right? So specification, parsing, static checking, compilation, interpretation, and all that testing, except analysis, because we didn't get that far because the project got killed before that. But we did most of the things. So we developed that from scratch. And the language, because the project was a research project funded by the DARPA, the language evolves to experiment with new features. The language itself has kept changing. The syntax has been changing, parsing, checking, everything was in flux. And our team was split into 3 parts. Language development by 3 teams in tandem. Every team was working together. Let's see, the first Spec team was with Eric Allen, me, and Victor Luchenko. I was the lead of this Spec team. We designed the language, the syntax, and everything, formal semantics. We had several versions of formal calculi. And the Spec, library team with Guy Steele and Jan Willem Messen, and they were writing Fortress code, really adventurous, weird library code in Fortress with using not yet implemented feature. So they were just they were writing something cool and asked us, the Spec team, to describe the language feature, introduce that. And with these crazy people, the implementation team had to implement that. So it was really fun. We had really good time working on that. And this language had really advanced features. So among many things, we had all those things. I'm not going to go into the details. And we had several versions of the verified, mechanized version of the calculi. And today, I'm going to briefly talk about just one feature of Fortress among many things, because it's kind of related to what I'm going to talk about, the weird semantics of solidity at the end. That's symmetric multiple dispatch. In Fortress, in many other object-oriented languages, they have overloading, method overloading, meaning that some method may have a name with multiple declarations. When you have, say, toString, the toString method can take any parameter with different types, right? Then when you have a call set of that, then you are going to find the most specific declaration for a given argument. And when there are multiple parameters to the method, then different languages have different approaches to pick the best method declaration. In Fortress, we took symmetric multiple dispatch, meaning that we are going to take the dynamic runtime types of all the arguments equally. So unlike Java or Scala, they pick the single dispatch because it's easier. But we think that symmetric multiple dispatch is much better because we are, for scientists and engineers, they're going to use binary methods. Then why do you think one argument is better than the other, right? So that's the main motivation behind symmetric multiple dispatch. If you want to have that, it's not that easy to prove that that's type sound. And as Yanis said, we were not really formalizing the entire full Fortress programming language, but we identified the core features to explain that. So before diving into the details, let me give you some examples. This is a class hierarchy picture. Let's say we have car class, camping trailer class, and this camping car extends both of them. So and then we have this overloaded method declaration with the name collide. So the 2 vehicles may collide, and when the first argument has type car and the second one has type camping car, then we are going to pick the first declaration. If that's the other way around, we are going to pick the second declaration. And we have 2 camping cars, right? Then collide with 2 camping cars. Which one is better? Both declarations are applicable to this call, but car and camping car, they are ambiguous, right? Neither is more specific than the other. Then at call site, you are going to stuck to decide the best method declaration to call. So we do have a set of overloading rules so that we can check the set of method declarations and identify possible errors at runtime at compile time. So static rejection of ambiguous method declarations. So by having this kind of set of rules, we can guarantee that at runtime, there are no ambiguous nor undefined method calls. So In this case, what's going to be the solution? Reject, that's one option. And what's going to be a better, fix this situation? There's a tie, right? We need a tiebreaker. So Fortress suggests programmers to provide a third declaration, which is more specific than the other two. So when you have this meet of these two declarations, which is more specific than both of them, then at call site, we're going to pick this, there's going to be no ambiguity. So there is a set of those rules. I'm not going to talk about the rules themselves. This example shows that when you have overloaded method declarations, multiple inheritance may introduce ambiguous cases. So next point is parametric polymorphism. If you add parametric polymorphism to this case, that's going to introduce new kinds of ambiguity. Let's see. So now we have a method, overloaded method declarations named sort. It takes a list of vehicles. The first one takes a list of cars, and the second one takes a list of camping trailer, right? And then, again, here we have a list of camping car. Then, which one is more specific when we have a list of camping cars? It's not clear, right? Now you can guess what we are going to require. So please give a more specific one than the other two. So that's our way of helping programmers to guarantee that there are no ambiguous calls at runtime and no undefined calls at runtime. So we had this paper in Uppsala 11. Actually, this topic was the last thing that the Fortress team was working on before some microsystems got purchased by Oracle. So that was January of 2010, and this paper was published in Uppsala 2011. But because this problem was so difficult, we had a type system, an imaginary type system, without any core language for Fortress. Just a type system with some static overloading. Type checking, modular, multiple dispatch with parametric polymorphism and multiple inheritance. With all these features, it's difficult to have a dynamic dispatch algorithm or any type soundness proof. So that was 7 years ago, and we moved on. And 5 years later, guy contacted me saying that, hey, I think I solved the problem. I have a great idea. Do you want to take a look at this again? And I was like, I need some students to work on that together. And luckily, I got 2 students. This is my undergrad, Jae-min Hong. This is a present for Alex, who met my students before. So Jae-min is an undergraduate student, and Kyung-hee, she was the first year of the master's study. And they took my programming language course, and they really liked type system from my course. But our lab was working on JavaScript analysis. And they were like, hey, I really like your course. I love type system. And why don't you study or research on type system? Oh, you know what? It's really difficult. And we got lots of funding from Samsung and Google and those industry because we are working on analysis. If we are looking at type system, it's really cool but difficult, but we may not get funding. And they were really interested in that. So I sent Kyung-hee to Boston during the summer for 3 months. And Jae-min and I visited Cambridge. This is Cambridge in US. And had fun, a lot of fun. That was last summer. And we worked on that, and that's now proved, and it's going to be presented at Popol next year. It's called the Polymorphic Symmetric Multiple Dispatch with Variance. And now we have a core language for Fortress with all those features, a nice type system, and dynamic semantics, and type soundness proof. Right? That's cool. And what did it require? This is the core language for Fortress, and you may not want to look at it now. And a set of typing rules, as Yannis said, we have so many figures in the paper, right? More, and many more, many more rules. But so now we are happy that it's out, but after that, we are trying to mechanize that in code. That's our plan. And I'm not going to show you the typing rules here, but just remember that, again, we have a set of overriding rules to guarantee that type soundness. There's a set of no duplication rule, meet rule. The meet rule is proposing the third disambiguating declaration. And this is the return type rule. So the return type rule is the key to guarantee the type soundness. Because even though you have these multiple declarations, you'd better have good relationship with this return type to guarantee the type soundness. So again, I'm emphasizing this to point out later with solidity. Okay, so this was our story with Fortress. And then JavaScript. So I've been experienced with ML, Scala, Java, Fortress, all those cool languages, and why on earth JavaScript? When I came back to KAIST, my students were telling me like, hey, let's do this JavaScript analysis. It's a cool language. Why is it cool? Everyone uses it. That's the language for web programming. Oh, really? And I was like, yeah, I've been through many languages, even assembly. Why not JavaScript? And when I first looked into this problem, my colleagues were like, oh, it's good that someone is looking at it, but why you? Or some people already working on this JavaScript was like, oh, welcome to the hell. Or there are many reactions. Matthias Felaisen, he was like, hey, why are you working on JavaScript? And after 1 year, he was like, are you still working on JavaScript? But 5 or 6 years later, when I gave a talk at Northeastern in his group, he was like, oh, yeah, you may, he told his students, like, this is one direction that programming language researchers can make differences in the real world. So what did we do? There is a language specification called ECMAScript, and there are many things. We were more interested in analyzing JavaScript web applications and finding bugs there. And there are several tools and outstanding tools that are safe by our team, and Thijs from Aarhus University, Anders Miller, and Walla from IBM. Julian Dolby is the main person behind it these days, right? So when we first looked at JavaScript, yeah, yet another language. I've been through that. Been there, done that. We're going to have a language manipulation. Get the syntax. I really liked Andrea's talk this morning because I wrote a parser for Fortress. We tried existing old parsing technique to parse the mathematical notation for Fortress. Nothing worked until we tried packrep parsing. And because of that, I'm writing parsers for JavaScript and Solidity and everything. But we had fun doing that. And we just looked at the JavaScript programming language like any other language. For we started with this formal specification of a JavaScript module system, and things like that. Having this lawyer, head of language lawyer. And while we are looking at the language semantics, the JavaScript is weird. I'm going to expand this to this because, again, I'm going to comment on this in terms of solidity later. JavaScript has a very weird semantics in terms of scoping. There are many other weird things. I can spend more than an hour on that, but the first one is that when you have a declaration of a variable, its scope is not from that declaration side. So it's just in the scope anywhere. So we had this hoisting to the top of the scope. And then it's mostly static scoping except one language construct called with statement. And there are many other things. So after parsing, we had to do this AST manipulation to go on with this traditional static analysis. After that, because JavaScript is usually embedded in web applications in HTML, we analyze the interaction between JavaScript and HTML. after that, because JavaScript web applications are usually interacting with native code, as Yanis said, we kind of took an easy path. We have this modeling for this native code and analyze the interaction between Android Java or C code with JavaScript. And finally, we gave up with this pure static analysis and dirtied our hands by having more dynamic analysis together. And having all this, we could find several errors, including Wikipedia, and that's my favorite example. We found an error in Wikipedia, we reported it, and the Wikimedia team fixed it right away. And they had the same error in 9 or so wiki blah pages. And yeah, there's another story, but I will skip that. So now Safe, the tool that we developed for JavaScript analysis, is being used in many places. And finally, Solidity. Why Solidity? So I thought JavaScript is the worst language ever. And now there's Solidity. Right? So several weeks ago, I went to ICFP. I talked with several friends there, and Adam Chulipala, he was like, hey, what are you doing these days? I'm looking at smart contract. He was like, what? Are you looking at smart contract? Why? I was like, oh, this is very familiar. Like when I first started looking at JavaScript, right? And Solidity, I think you've heard of many attacks because of the smart contracts. So it was like a hype for several years. And on one colleague at KAIST, he asked me or suggested me working on this smart contract and blockchain thing for years. And I was like, I'm not interested in that because I don't like that hype. And I don't see any actual thing there. And I don't like those promoting Rusts and people are so, enthusiastic about this cryptocurrency. I'm not with that. So I was saying no till the early this year. And then when those hypes are kind of going away, techniques are coming up, and smart contracts are like programs in new domain. And we've been looking at program analysis, finding bugs. We've been looking at binary analysis a bit. It was really difficult. Building control flow graph from x86 is really crazy, right? And now, if Ethereum VM, Ethereum bytecode is really tiny compared to x86. And there are many cool features there. And there are money, and I don't really care about the money, but there are people who care about money and who use this smart contract. They call that contract. How come? How can they so optimistic to believe that? So, as this one of the top security researchers, Bruce Schneider, said, all those attacks by smart contracts are not because of the fault in cryptographic failure, but because of the vulnerability in smart contracts. So again, it's just like JavaScript, right? In the beginning, when JavaScript was first developed in 1995, the language was developed by a graduate student in 10 days who was not majored in computer science. For next 10 years, until 2005, people were like, yeah, it's a small language. It's not really a programming language, it's a scripting language, right? But after that, it's everywhere, and the programming language researchers came in, but it was too late. There were several variants, like TypeScript from Microsoft, Flow from Facebook, and many other efforts didn't fly because JavaScript developers were like, they are not JavaScript. Right? They did not really appreciate the effort. So there were two approaches. One approach is to have a better language for JavaScript. It didn't really fly. TypeScript is really used well these days for IDE support. Some usual help. And the other bigger camp is to analyzing JavaScript applications and finding bugs. That was my take on JavaScript research community. And now, Solidity or Ethereum VM, they are following the same trail. they try to formalize the semantics. This famous yellow paper is trying to formally specify the semantics of Ethereum bytecode. And Fstar in plus 2016, Fstar was used to formally verify a small subset of the Solidity programming language. A little bit of background is that the blockchain community, there are many platforms, Ethereum VM, Tezos, Bigtelson, and Liquidity Language, and IOHK that's backed by Haskell, and a lot. Right? And among those things, at the moment, Ethereum is the #1 platform. And Ethereum is just one platform, and they have this virtual machine, like EVM, Ethereum virtual machine, and they have a bytecode. And those smart contracts are in bytecode form, and they are embedded in transactions in that blockchain world. Right? And programmers are not code in the bytecode. So there are several source languages, Solidity, LLL, and Viper, a different Viper, right? And then they are compiled down to Ethereum bytecode. So yeah, Solidity is the source language that's compiled down to Ethereum bytecode and being used in that VM. So in this Fstar work, they formally verified Solidity, not the Ethereum bytecode. The famous Oyente, CSS 2016, they proposed a symbolic executor for Ethereum bytecode, Oyente, implemented in Python. This is not that bad. It's being used a lot, but there are many rooms to be improved. And after that, in 2017 post, they surveyed very small fraction of attacks known by then in terms of, in the level of Solidity, the source level language, Ethereum VM level, and blockchain level. And now, 2018, papers are like blowing. So in February, NDSS, there was a tool called Zeus, or whatever you call that. They took Solidity code, and they didn't compile that to Ethereum bytecode, but they compiled that to LLVM bytecode so that they can take advantage of the existing tools for LLVM. It's a cute idea, but because they have that limitation, several features of Solidity, like assembly block and things like that, cannot be compiled down to LLVM bytecode. But it's a cute idea. After that, again, in April this year, this is claimed to be a complete, the best formal semantics of Ethereum bytecode. And there are two more conferences that I'm going to show. In August, Unix security, there were 4 papers about smart contracts. And this week, where's Peter? Where are you? Yeah, over there. He presented Securify from ETH at CSS. So there are many tools and research, like I have this thinking that it's kind of mimic that we've gone through with JavaScript. All those formal approaches, all those new programming language proposals, and those tools to find bugs. And as Mark, did you say that? Like finding bugs is like a glorious grab. Like for a given set of patterns, or for a given or well-known list of bugs, we can find them. But what about new kinds of bugs, right? So for the remaining time, I'm going to tell you what we are working on in this problem domain. So there are many people, like when Adam was giving me a hard time that I'm working on smart contract, I was like, no, we are interested in this problem. It's a new domain, and we can use our, our experience with that. And he was like, yeah, everyone says so. These days, many PLO researchers are working on this smart contract. And why you? And what are you looking at? So even my own students, they are like mathematicians, and they like formal methods, and they are like, really? Why are you interested in smart contracts? So I was thinking, why our group is looking at the smart contracts? Because based on our experiences with various kinds of languages, when we looked at the semantics of solidity, it doesn't make sense. There are many places that doesn't make sense, and today I'm going to tell you only two things that I had anchored with those two languages. Number one, scoping and declarations. This is an excerpt from the Solidity language specification. A variable declared anywhere within a function will be in scope for the entire function, regardless of where it is declared. This happens because Solidity inherits its scoping rules from JavaScript. Why? Right? Remember this picture? We had to have this weird hoisting. So this little module is being used really a lot by the other tools like this K framework, and they have this JavaScript analyzer. They use our front end, safe front end, to use that hoister. Because it's a little thing, but that really hurts analysis. And now they realize that, and they're changing the semantics. So since 0.5.0, Solidity will change the semantics. So why did they use the JavaScript semantics? I don't know. It's a mystery. Another thing, overloading, right? Overloading and multiple inheritance. Again, this is an excerpt from the Solidity specification. It says, return parameters are not taken into account for overload resolution. Really? Do you remember this return type rule? If you do not check the return type, say when you have those two overloaded method declarations and when the parameters have this subtype relation, you need to have that in the return type. Otherwise, type soundness will be broken, meaning that even though the type checker says okay, you are going to have stuck code at runtime.
This is for overloading, not for overriding.
Overriding, meaning the return type should be the same. Overloading, meaning that still you need to have some relation between these return types. Right. So maybe the spec is not complete and the implementation itself, the compiler itself may be correct, but there are rooms to look at. Another, a little bit more weird thing is that multiple inheritance and linearization. So if you are familiar with this multiple inheritance, the typical famous problem is diamond problem. When you have a class A and two subclasses of A, B, and C, and then the final class D is extending B and C, it's a diamond. When there are some fields, states in them, then this bottom class is in trouble. Which one am I supposed to use? This is a really famous problem. So C++ has this multiple inheritance, and it, as usual, it lets programmers to do whatever they want to do. There are like 3 semantics to do that. In Fortress, we had a way to reject any possible ambiguity at compile time. In Solidity, it says Solidity is similar to Python in that it uses C3 linearization to force a specific order in the DAG of base classes. What does that mean? Let's look at this small example. Here, Solidity, contract is like a class, and contract owned, and there is a subclass of owned, mortal. Yeah, I didn't write this owned. Oh, yeah, let's start from mortal. And there are 2 subclasses, contracts of mortal, base 1 and base 2, and then final. So this is diamond, right? And even though final extends base 1 and base 2, and base 1 extends mortal, base 2 extends mortal, and there's no relationship between base 1 and base 2, because Solidity uses that C3 linearization, there is an extension, there is an inheritance between base 2 and base 1. Why? Because final said it extends base 1 and base 2. So this is going to be more specific than base 1. Meaning that when you define your contract, you didn't see that relationships, but later, because of the users of those two classes, two contracts had this post-factor relationship, it's not really composable, right? So, but this is again from the spec of the solidity. It says that, mortal has this kill method, and base 1 will call mortal the kill, base 2 is going to call that again. Then, because it's going to call this one, it does not call this base 1's kill method. It's a problem, according to the solidity semantics. So the spec says, instead of this explicit call of the contract name, you'd better use super, right? Meaning that when you call final dot kill, it's going to call base 2's kill. And then, because super of base 2 is now base 1, it's gonna, doesn't make any sense, right? And then base 1's gonna call this kill method and then mortal. Do you like it? Maybe this solves that weird problem that Solidity had, but this one opens to the gate to attackers. So it's another example. This is from some blog post that you can take a look at that later. I'm not going to go into the technical details, but what it says is that, again, same diamond. We have crowd sale contract and kept crowd sale and whitelisted crowd sale and whatever. And because of that weird inheritance relation, attacker can have bypass some checks. You can take a look at this blog post to understand the situation. The main thing is that because each contract was developed modularly and it only understands its parent relationship, and there is a post-factor relation between that, there could be some holes. So, what is C3 linearization? So my student, one of my students, he's a good hacker. He has a good sense of hacking, finding holes, but not yet well educated with programming languages. So he was like, it's cool. And he was explaining. Then I was like, why? What's happening? And he was like, it's so cool, C3 linearization. What is it? I don't know. So I looked at the related document. It says that, C3 linearization is from Uppsala 1996, the language called Dylan. So Dylan was proposing this rule to solve the problem in clause, really old language, meaning that back then there were not that many static type systems, and clause and Dylan, they have specific situations that classes and objects are open. And they are dynamic languages. They can add functions during runtime at classes, and they can have post-factor relationships, inheritance relationships between classes during runtime. Then it's really difficult. And they really need some specific ordering between them. But Solidity is not like that. It doesn't need it, right? It doesn't need all that relationships. So those two are just simple examples that I can explain not without spending too much time, but there are many other features. Yes?
Yeah, so do people use multiple inheritance in writing smart contracts?
Very good question. Do people really use the multiple inheritance? That was the first question that I asked to my student. And he was like, yes, a lot. Because, one thing is that, as Yannis said, there are lots of smart contracts, especially this Ethereum contract. And there are many copy and pasted code, duplicates, not only duplicates, but copy and paste and some small changes. And there are several guidelines using multiple inheritance. And why multiple inheritance? Code reuse. Because, especially with the Ethereum VM, this use of runtime is really expensive. And they have this concept of gas consumption. So they'd like to have some library and some code reuse that's really, suggested. So that's a lot. Yeah, that happens a lot. So what we are looking at right now is to see whether changing the order makes the differences in the actual results and things like that. Okay, so there are many other questions, good questions, like why Ethereum? Do you really believe in Ethereum? How about EOS? And WebAssembly may be the next language. And there are many languages out there. And oh yeah, Silica and Scala. So which language level? Source level? You know, compiler has bugs. We know that. And how about just bytecode? So we are looking into bytecode analysis as well. And what problems? Again, this reminds me of the early stage of JavaScript analysis. When I met my friends like, Julian or Anders or even Ben, we were like, what are bugs in JavaScript? They do not care, right? It doesn't crash. The main benefit of using JavaScript is it does not throw exceptions because there are so many implicit conversion. There's one chapter of implicit conversion in the JavaScript language Spec. So what are bugs here? Is it type related or resource related or security or privacy? They are all related questions. So we are interested in analyzing smart contracts, especially Solidity, because the semantics itself is weird, and we'd like to let people know that's not really solid. Right? It's not solid. And you'd better know what you are doing with this language. So this is our team. And my last slide is pictures with our visitors at KAIST. Here's our own Alex over there, right? And Rustin. Here's Xavier Val, right? Yanis mentioned him. And Ron Garcia. And this is Ilya Sergey. And we have Hongsak at KAIST. And this is Atsushi Garashi. So at KAIST, we are really interested in working with many cool language researchers. And if you have a chance to come visit Korea or any Asian country, please let me know. And we can invite you and have some interesting, fun time. Thank you.
Any questions? More questions? Yep.
The linearization policy, it may have some side effects, but it's not unreasonable. I think Scala, for instance, does the same for mixins. So it's a standard thing.
So the question about this linearization, actually, Scala has that in terms of when it extends traits. Right? It has this, right. For traits, it has this multiple inheritance and they have the ordering, but they do not have this extra inheritance between them, between those traits.
They do.
They do?
The exact same behavior with the super calls. You get the exact same behavior.
You get exactly the same thing.
Ooh, I need to double check. Yeah.
It's not in principle that it may lead to bugs in Solidity. That's not.
Yeah, that's a good point. Yeah, thank you. Right, but one thing that I just wanted to add is that not only this blog post, we had some we had some requests from the people working on smart contract company, and one example is that they asked us, like, do you have this automatic detection of bugs like this? And they had to pay lots of money to some audit company to find this bug. They actually had this bug from the developers. So again, as Yannis said, the specific semantics may not be wrong, but it's not possibly unintuitive. Yeah, it's arbitrary, and it's really error-prone for programmers. Yes.
Okay. More questions? If not, let's thank the speaker again.
Thank you.
We have a break.